Excellent, excellent. So as Andy said, I'm Mona Sihota. I'm the Network Technical Head, formerly known as Professional Head for Drainage and Line Side. Um, been head of drainage, oh gosh, now since 2015, and head of line side since 2018. I want to talk a little bit about some of the challenges, interesting facts and figures, and improvements that we've got going around Network Rail when it comes to drainage and in context of extreme and adverse weather events. So, come on screen, there we go. So, drainage. So why do we need to change? Or is it just basically, do we need to change because we've got more extreme and adverse weather and that things are going bad? Well, we have legacy assets. So for those who have got quite a few years of experience, you may be familiar with drainage on the railway. And there are two parameters that we normally design for. It's 1 in 25 or 1 in 50 rainfall events. That's what our standards say. So your primary routes are for 1 in 50 and your secondary routes are for 1 in 25. Since pre-2015, there was no head of drainage in Network Rail or Railtrack or BR. So the role was only created post that, but pre-2015, we approached drainage in two aspects. There was drainage for track and there was drainage for earthworks. And then actually there was drainage for buildings, which is still separate and built. And then there's track drainage, and everyone was sort of looking after their own part. So it wasn't really connected. As we move forward with time and we got to know what's coming around the corner with climate change and extreme and adverse weather, the term climate change predictions have actually changed to projections. We are no longer predicting what is happening, but we are projecting what is happening in the space of climate change. And we are seeing that we will have more intense rainfall. We're looking at 20% more intense rainfall in summer and 25% more intense rainfall in the wintertime. And we're looking at projections of saying that there's going to be about 7 extreme weather events per year. And we saw that last year for sure. And that is what the what DEFRA and the more sort of world bodies are looking at, saying when it comes to projections with climate change. So that's kind of scary stuff. And those the patterns aren't changing. We're still going to have summer. We're just going to have a lot hotter and drier summers, and we're going to have convective rainfall events, which are those rainfall events that happen during the summer. They're quick, they downpour, and then they move away. And over winter time, we're going to have colder winters and wetter winters, as mentioned, with that 25% uplift. So still going to have a season. We're still going to have seasons, but just more intense. So that's not so bad. Maybe it's okay. Maybe we can cope with what we've got with drainage. And it's only just a recent thing that our drainage systems are being challenged because of climate change, or whatever reasons we want to align to that. So I did a little bit of a review back, and this is on incidents. These are incidents where RABE or the ORR have investigated these incidents. And we went back to 2000. There were some in 1940, but I'll get to that one in a second. So what we really saw was going back to about the year 2000, so we're talking 23 years ago. We are looking at every 2 years or so a derailment related incident that has a connection to water or rain, or flooding or washout and earthworks washout due to extreme weather event. And what we're seeing is that that frequency is there, and it's being looked at, and we're seeing every couple of years. And things are more recently getting worse. The worst being Carmont, which was the 12th of August 2020, which resulted in a derailment that led to 3 fatalities on a train that had 20 people. So that's something to sort of hold in your mind when you're looking at numbers there. So these incidents that have happened and the learning that the recommendations and the findings that have come up, we looked back and said, is there some commonality? Is there something that's looking, pointing towards things that we could learn from? And so at the time of creating this little root cause analysis, Carmont is not on this one because at the time it was still under investigation and we were still putting our findings together. So this was data as of 2021. We looked at the RAID reports and the ORR reports and tried to summarize as best as we could some of the findings and the relationship of those findings to those incidents. And you see on the sort of the green and the blue column an overall sort of start of the incidents, and then we move forward to oh, I'm hearing. Oh, sorry, I'm hearing somebody. Can you go? Please be on mute. Thank you. So what we found are the findings that you see here on the screen, and then we move forward towards saying that there's sort of incorrect assessment, which leads to a lot of issues there. Communications, designs, maintenance. We move forward and saying, well, what led to those? Well, basically increased drainage runoff. And maybe structurally the assets were blocked or broken. And those things lead to the big sort of circle that's got all the numbers at the top, which is basically that the drainage asset system was either not performing or the capacity was exceeded. And because of that capacity or the non-performance of the drainage system, it resulted in either an earthwork failure or it perpetuated a track defect. It amplified that track defect, which then led to the incident occurring, the incidents which are specifically listed there on the very left-hand side. And so using this information, we thought, where is it that we really need to focus on making a big change so that we could start really a step change in the way that we approach drainage and looking at drainage's relationship to other assets like tracks, structures, earthworks, but also drainage in the railway content. Because drainage was always used to be referred to as the child asset, the thing you sort of do if you've got time. But I wanted to sort of really challenge and look at that. And so moving forward, there we go. What we know is that functioning drainage supports the optimum performance of other assets. If you've got good performing drainage, which is managing the water, basically is collecting and conveying the water, you will have optimum performance of your earthworks because they will be stable. You will have optimum performance of track because the formation will be dry. You will be on a solid ground. Your structures, I'm talking culverts, tunnels, retaining walls, will have solid ground as well and will not be affected by the forces of water pressure and hydraulic pressure on them. Signaling, I mean, any sort of mechanical, electrical assets don't really like water, don't like being underwater. And so, again, making sure that we keep the water away from those other assets and keep it flowing because water does flow. We're part of the life cycle, a water cycle. We need to move that water away. More recently, with extreme and adverse weather event, we're seeing too much and then we're seeing too little water. And now we're seeing the summer that we had last year with the very, very high temperatures. We're seeing desiccation in the ground. We were seeing water porosity affecting track geometry. So where the water, there's just no water there, you're seeing desiccation, you're seeing trees dying and having early leaf fall. So not enough water is also an issue. And one of the things that sort of resulted in is this sort of thinking that actually, you know what? Drainage, yes, the purpose of drainage is to manage and convey water, but drainage itself alone does not manage and convey water. The network, the railway infrastructure has a relationship with water in its own right, and that we needed to sort of look at it as a national issue as well. Look nationally at where we've got water and what we need to do with it, and where, and also then specifically for drainage. So if you bear with me and being a very poor presenter, I'm just gonna stop presenting for a moment because I would like to share a video with you to show you a little bit about what we're doing in this space, and I'll start sharing in a second once this is all set up. Share with sound, this should work. Sorry, if I don't talk out loud, it doesn't seem to get in my head. So you should be able to see a video and that I'm about to play, and you should be able to hear the sound.
Introducing Network Rail's water management strategy.
Yes, I got a thumbs up.
This strategy is going to change our approach to water management. But before I tell you more, this is why we need it. Climate change is happening now, making the consequences of extreme and adverse weather a reality for all of us. Flooding and droughts already cost Network Rail millions of pounds a year and are only likely to get worse. From landslips to electrical failures, weather-related incidents affect the safety and performance of the railway, resulting in penalties, delays, poor environmental impacts and a disrupted service for our passengers. But we can improve. Network Rail is committed to running a reliable railway network. To do this in today's world, we need to prioritise water management. This means dealing with the water that affects all of our railway assets. We need to grasp the wider challenges of water scarcity, polluted water, and the potential benefits of excess water, in collaboration with our neighbours. We've developed the water management strategy consisting of 5 principles. These are: take a holistic view, be resilient, use less and recycle, keep it clean, and unlock wider benefits. We are the first in the transport industry to develop a water management strategy. It's an opportunity for us to demonstrate our proactive leading approach. As the 4th largest landowner in the UK, we can make a profound impact. Water affects all of us on the railway. Every asset group and all life cycle activities, including inspection, maintenance, design, construction, and asset management, have a part to play. We all have a responsibility and we need to start today. So, how do you make a difference? Start by engaging with a water management strategy. Go to the My Connect page for more information.
Great. So for those that aren't Network Rail, what that is basically an approach to our water management strategy. It is available. It's only sort of internal at the moment. But we are looking to go forward and go external with it. So let me go back to my presentation now, and oh goodness me, share screen. This should work. So you should see the presentation again. Hopefully, I'm just looking at Andy for a thumbs up. Slide decks back up. Yep. Okay, great. Thank you. Thank you. So for those that don't know me, I've got a sarcastic sense of humor. So drainage is easy, right? Once you've mastered the complexity of it. All right. And I'm sick of people saying that drainage is just easy. It's a copy and paste, doesn't really need much thought to it. It actually is quite complex in its own right. And it's complex when we do it right. So drainage is a system with multiple components. Drainage is the system is defined as multiple inflows with one discharge point. You can have multiple systems across one catchment, or you could have one system over many catchment. So what you're looking at is the drainage run from where all these inflow points come, and those inflow points can be surface runoff from fields. They could be your own groundwater coming from within. They could be piped in physical connections like what we would have with highways, maybe highways discharging into the railway, and then we have that as an inflow point. Hopefully it's managed in a physical connection, not just being dumped onto the track, but that's hope that we have got going forward. So that's the inflow, anywhere you've got water flowing into. And you only ever have one discharge point because that's the end of your system, where water leaves our infrastructure, our accountability, and goes into the next downstream riparian owner's accountability. So that's the system. There are differences when it comes to us understanding what drainage is. There's hydrology, there's hydraulics, and geohydrology. Each is its own science, and each has its own sort of models and equations and methods of viewing the world. So hydrology is the study of water. It is a very probabilistic method and approach to looking at water, because you cannot engineer rainfall. You are trying to predict rainfall and where it's going to go and how much is going to get saturated. Hydraulics is engineering, and we've got equations that we use and materials that we use, and we use dimensions, and we plug those into our formulas to calculate what we need and what we want, either coming in or coming out of our drainage system. And geohydrology is how water seeps through the earthworks, and what is absorbed in the soil, how much water is it absorbed, how much runs off, at what point is it too much water that the whole thing has a washout, what different soil types react and interact at a molecular level with water. So it's quite a complex topic in its own right. And those three sciences sitting together talking about drainage are really what we need in this space to have proper good drainage design, drainage studies. So I talked a little bit about the engineering versus the probability. Probability is really coming from how much rain, that's the input parameter that we need for our designs. But it's more than just the rainfall event. We need what type of land is adjacent to us. What type of land is the drainage sitting on? What type of soil is it? Is it clay? Is it sand? Does it have natural porosity and saturation, or is it all running off? How does it behave when it gets wet? Does it expand? Does it cope well with water or not? Topography, so basically slopes and gradients. We're talking about the contours of the ground and how that affects your flow rate, or whether there's retention in ponding and attenuation that way. And then also where we've got catchments, and knowing that we've got a catchment that catches the water that we want holding, and the water that flows towards us, aka the water basin. So looking at those things, when we look at the engineering side of it, and my apologies that my assumption that the audience are mostly engineering or of the technical background or engineering background. For those that don't know, our go-to, our Bible for hydraulic is the Manning's equation, and we use Manning's equation to calculate. Often we use Manning's equation to, if you have a pipe, depends on what you have. If you've got a pipe of a certain diameter and a certain material, plastic, corrugated pipe of a certain diameter, you can use Manning's equation to calculate what its maximum discharge rate is, how much water can flow through that pipe. You flick it around the other way. If you have how much water is coming towards you, you can back calculate then to find the area, your wetted perimeter, and that's where you size the pipe depending on the demand put onto your system. So we use quite a few industry standard products, British standards when it comes to pipes and channels. We use highways. We have our own standard detail drawings that we use based on sort of our knowledge and the best experience that we have at the time. We've got a lot of experience in track drainage, and we have a lot of experience in earthwork drainage, but not together. We have them separate, and there is, believe it or not, a different approach to both at the moment within Network Rail. Even when it comes to our engineering of those two types of drainage. I'm not going to call them drainage system, because drainage is a system and it includes track and earthworks drainage. It's the run. But where they're located, track versus earthworks. There's a lot of experience in the ways that we have been doing things. I'm not saying they're necessarily correct. So I put up Manning's equation and I said, right, Q's the thing that we're trying to get. But when you're designing a system to start with, you want to know what Q's coming at you. Q's the flow rate. Sorry, I got the US version there, but cubic meters per second. How many cubic meters per second are coming at me? How do I know what I'm designing for? What is my system, my drainage system's capacity and its capability? So up until 2018, when we redid the drainage design standards, the drainage design standards previous to 2018 didn't really talk about catchments. It sort of lightly said you could use local knowledge and what you know of the area. When we redid the drainage design standard, we popped in and said, no, you need to understand the catchment. You need to use catchment data. You need to use a modeling. And the recommendations at the time were flood estimation handbook. But there are other models that you could use to understand, based on the catchment size, how much water is coming at you. So seems easy enough, but there's a cost to it as well. And that cost, when you're doing simple drainage designs, is probably one that we don't want to bear. We didn't think that it was worth it. And so we used our past experience and said, this is the designs that we need to put in. However, in a post-Carmont world, that is no longer acceptable. And so one of the things that we've done to deal with understanding how much water is coming at us, and now I'm talking about normal rainfall, put on top of that your extreme and adverse weather rainfall, how do we understand how much water is coming towards us so we know how actually to design our systems? And so again, if you wouldn't mind bearing with me while I switch to another video, so that I can show you what we've done in the space of catchments. I hope that you find this very interesting. I personally do too. So I would, I'm just a geek for water. Let me share my screen again. Include sound, include sound. There we go. You should now hopefully see a video that's about to start playing. Only 2 minutes. Thanks, Andy.
Surface water runoff has potentially devastating consequences to the railway. At Network Rail, we need to manage this threat across our infrastructure to ensure we operate a safe and reliable service. This is why dependable data is so important. It helps us to make the right decisions to protect passengers. Now, for the first time ever, we have a data set that maps rainfall catchments across the entire railway network. It's taken more than a year to produce and encompasses more than 100,000 individual catchments, taking into account various catchment characteristics, from catchment area to soil type, in order to understand potential surface water runoff. This dataset can provide the likely amount of surface water runoff flowing towards the railway from each catchment for a given rainfall event. It relies upon the Flood Estimation Handbook, an industry-standard statistical model developed to understand surface water runoff peak flows from UK catchments. While the methodologies used aren't new in themselves, this is the first time we've been able to access this information for the national rail network at the touch of a button. The dataset is available as a map layer in GeoRhythm Viewer. A water threat index derived from the Flood Estimation Handbook model and other critical attributes such as crop cover and catchment slope provides a colour-coded ranking for each catchment. At a glance, the user can understand the catchments that potentially pose a surface water threat to railway infrastructure. This helps asset engineers swiftly decide which assets need improvement first and where to install new drainage systems, making budget allocation easier and enabling rapid comparative assessments of which catchments are potentially more troublesome. Now it's possible to view a section of track online and contrast the relative hazard posed by adjacent catchments and how these compare with other catchments across the network. The dataset also provides a great starting point for more advanced analysis, assisting asset management teams and designers in making informed decisions and facilitating good engineering judgment when developing new capital schemes. In addition, the dataset is also being used to build new asset management tools currently under development, such as the Streams tool. When used in conjunction with programs such as this, the dataset has the potential to help provide a complete drainage system overview from inflow to outflow. This allows engineers to understand the current and future ability of drainage systems to protect the railway in the years ahead.
Just let that finish. Okay, back to the presentation. So when I mentioned that catchments are key, they are super key. They are key. oh goodness me. Share. It would help if I shared. There we go. So for those who love formulas, here's a few more, and I promise this is the last slide with formulas on it. So I've mentioned Manning's equation. Manning's equation is our hydraulic way of calculating the work that we've got. Sorry, to calculate the sizes and the wetted perimeter of our drainage systems. Catchment is different. This is based on a probabilistic regression model that allows us to predict how much water is coming towards us at different rainfall events. It is probabilistic. The one that we use is FEH, which is the equation at the bottom. And this isn't something you want to sit and do by hand. This is all done by computers, and we model it out that way. So it's not something that necessarily we would hand calculate out. Now, so what we've done is we spent the year mapping through where are the catchments. That's the first bit, the space. What is the peak flow rate coming through it? So that tells us what the demand is on the drainage system, and we can look at normal rainfall event, a 1 and 2 event, and say how much water is coming at us. That's cubic meters per second at a funnel point of that catchment. And we're able to take that water and say that Q value is what's going to go into the drainage system. And then we can calculate back to say, now I can design my system. But the issue is we already have drainage systems in the ground. So retrospectively, we can look at those drainage systems which are not able to support the demand put on them now. But we can also look at how resilient we are for future rainfall events. And I'll show you in a second a little bit more detail there. We looked at, there's about 100,000 catchments mapped nationally for the whole network. And we've used QMed, which is the median annual flood value for each. The data for those that are Network Rail is available in GeoInterviewer, which is a tool that's available for everyone in Network Rail. If you are not part of Network Rail, you can ask for that GeoInterviewer data via our Freedom of Information Act. If you know, request for information, which is request for information FOIs. You can request information if you've got your ELR mileage or your postcode or your geospatial location. You can say, I would like the catchment layer for that. And that then is exported in a GIS sort of file if you have that. Worst comes to worst, someone can give you a screenshot. You don't want a screenshot though, you want the data that's behind it as well. So I'll kind of go into it a little bit. So I gave you a quick overview of one of the drainage systems. It was a little image that I showed in saying drainage is a system, links and nodes that are connected. And in this image that you're seeing, you see the links and nodes that are here. And this is a very good example of a drainage system mapped out on our GeoInterviewer on a particular ELR, the Bravo Alpha Echo 2 line in this particular example. And I selected the catchment that is feeding into that drainage system, which is the one that's highlighted in blue. And when I highlight that, I get additional information. And the additional information that I get for that catchment is the square kilometers of the size of the catchment. I mentioned QMed. So that's your sort of normal flow rate. So on this particular catchment, normally it's about 0.4 cubic meters per second. That's not so bad. But as you start to move up the chain, so Q5 is 1 in 5 rainfall event, a 1 in 30 rainfall event, a 1 in 50 rainfall event. And remember when I said that we normally design primary routes to 1 in 50. So when we're designing, this is the value that we should be designing, Q50. But if you want to make your drainage system resilient, you start to look at 1 in 100 rainfall event, 1 in 200 rainfall event, 1 in 500 rainfall event. Because in the standard that we recently updated, we've asked for Q100, a 200 and a 500 event to be modeled to see what would be the catastrophic impact of such a weather event. And then down at the bottom, what you also get is a Q100 plus 2050 climate change prediction. So basically from Q100, based on climate change predictions, sorry, I said it now, not predictions, projections, we're looking at an increase of 1.6. And then you're looking at 2080 climate change projections at the moment of cubic meters per second. Somebody asked me, they said, right, what's 1 cubic meter? If I was trying to imagine 1 cubic meter, what is that? And we were trying to visualize it, and someone was like, I think it's like a bathtub. If you have one bathtub full of water, that's 1 cubic meter. So when you start to put it that way, that's a lot of water per second that is flowing through this particular catchment. Now, I was a little evil because I specifically picked this catchment. It's one of the larger ones. There are smaller ones. So I wanted to zoom out and show this catchment in respect to others. And so what you should see is the catchment. I was zoomed into this little section, but that's quite a large catchment. There are smaller ones. You can see here, there are smaller ones here and here and here. I can't hear you, but how about I ask you, anybody want to hazard a guess why this catchment is the weird shape that it is, and what particularly might be of interest in this area to lead to a catchment of this sort of shape and size? I won't say anything. I'll do it in the Q&A session just to give you a little bit of a brain tease while I continue to talk. So a purple lined catchment is water that is flowing towards the railway. And these are pluvial catchments. The way to think of way that I think of so there's pluvial and there's fluvial. Pluvial, rainfall creates ponds. Ponds starts with a P, right? So does pluvial. The other type is fluvial, and those are shown here in sort of this mustard color. Fluvial is river flows, and it flows towards natural water courses. So I think of rivers flowing, starts with an F. Fluvial, flows like the rivers. Pluvials, pond, because of rainfall. So that's the way to think about it. So purple coming towards us on the railway, your pluvial, and then the orange going away. I picked this particular image as well because also this is of interest. Very recently, there was a structural wing wall at this location that collapsed. And ironically, it was just at this location here. I don't know if you see my cursor on the screen, but it's just at this location. And when I heard about the location, I thought, oh, I wonder what the catchment's doing in that area. This is of particular interest, this location, because not only do you have water coming through, you have water flowing away. So you have a hydraulic flow, in natural hydraulic flow, even before we put any roads and retaining walls and wing walls in this location. So that creates an interesting challenge in its own right in this space. And if you recall at the start of the presentation, I said when it comes to water and water management, it's railway infrastructure. It goes beyond drainage. This is obviously very important for drainage, this information. But if you are designing to put in a new signaling substation, an electrical substation, and you know the location that you're putting in, have you considered the surface runoff at that location? Is it a lot of water flowing in that area? And therefore, when you're putting an electrical building, is it going to be in an area that's going to be prone to flooding, or is going to have water around it? And if you have an option, why not move it to a place that's drier? And if you can know that at a very quick glance, as you can now with catchment, that's going to help you with your whole life cost of your asset. But also, let's think about track. where we have a lot of surface runoff and we've got track geometry problems that maybe aren't really clear to us, have a look at the catchment in the area. Do you have a lot of water flow through the area that might be contributing to wet beds, to track geometry or cyclic top? Because the formation underneath is part of a hydraulic flow that's going through that area. And so tunnels, culverts, a track signaling system, the railway infrastructure as a whole is impacted on water. And so catchment is basically mapping the water that's flowing towards the railway. When I showed you the Q values, that's where the drainage designers get really excited, because that's the data that we want to use specifically, and then we never had before. Or you would have, but you would pay a designer to do a catchment design specifically for the area in particular. Now, so when it comes to drainage and us looking at extreme and adverse weather events, this is key, because this is not only looking at normal weather, but we can start to predict we can start to design for the future projected climate change, water levels coming at us. But we can also look to see whether we are resilient, and where we've got high risk locations, we can start to look at where we're going to design and improve those, or build more resilience into our drainage system. Yes, network rail and drainage are doing a lot of work in this space, but this is a bigger issue. Water and water management is a bigger issue, and extreme and adverse weather is more than just drainage. So one of the things that we are looking at is catchment communities. And these are catchment communities. If we're being flooded and we're in a catchment, there are others that are getting flooded that are also in that catchment. And they could be highways, they could be councils, they could be water companies. And so we're starting to talk to the other larger organizations and saying, where are you having your water problems, and where are we having water problems? Let's come up with solutions that support both. And that means joint funding, partnership programs or projects. The other thing that's really been out there with looking at environment and sustainability are blue-green infrastructures and designs, where you use vegetation to support managing the water that's coming towards the railway. So if we can plant trees outside of the railway, that will pick up some of that surface runoff, or we can create natural berms, and that would divert the water or hold it in or flow it in a different way. That's much cheaper than us digging up the railway and putting in piped systems. So blue-green infrastructures is really a big thing that is coming, and we're being pushed a lot for that. It supports carbon reduction, and it supports more green, sustainable solutions. We've got more remote monitoring equipment and data acquisition now out with tools like Track Water. We've got new systems that we're putting into our buried drainage system so they can alert us when water is rising. We've got a mobile map app, which actually has a map on it now. It's for our inspectors and maintenance teams to use, so that they can collect condition data much more easier on the connected drainage system. Instead of them looking for that drainage system, it'll be mapped out for them, and they're able to quickly collect condition data. We are improving our risk models that look at that are predicting where the flooding will occur, are also going to look to predict where we're having earthwork failures and also wet beds. And it's using it's using AI and machine learning of past data, but also the catchment data, rainfall predictions, and bringing all that together to look at where we're going to be where we're going to have our problems. And that's helping us get ahead of the problem, be more proactive. We're building up drainage competencies. They are identified and defined and uploaded in our competence management system. And to support those competencies, there are training courses, of which, of course, PWI have a training course. Network Rail are coming up with their own sort of e-learning modules as well. There are lots of training courses available. If you want a training course on FEH, there's a one-day course done by Wallingford that train people on how to use the FEH model to understand risk modeling or flood modeling. And I think the biggest thing to make improvements going forward really is to challenge and ask questions. Are we doing the right thing? Is this correct? Is there another way of doing things? especially when we have repeat failures and repeat problems. We really should push forward and challenge the status quo, instead of accepting things as they are and just doing it again and doing it again. So thank you very much for your time. I'm going to now close and stop presenting so that I can see you all and take any questions. Thank you very much. Andy, you're on mute.
Yeah. Okay. Can you hear me now? Yeah. So Simon Smith came back and said that that catchment you showed was actually over the top of a tunnel.
It was
So
spot on.
it was high. That was a
Yes.
hill. So
Yes.
Well done, Simon.
Yes, he gets the sticker. Yes, he's correct.
That's it. So Sankadev, who's a guest, said, how is QMed related to high flood level, and should track drainage designs be to QMed values?
Okay, so the problem, the challenge that we have when we look at flood levels is we don't have height. Now, the Environment Agency are looking at river flooding and coastal flooding, and they are looking at putting heights in. We just don't have enough data, nor do we have the sort of the computer power to do the modeling at the scale, at that level of scale, because our corridors are so thin when it comes to the overall river catchments. And so if you're looking for height and how much water is coming through, please do look at the Environment Agency. They do have flood modeling, flood maps. That would be the best place to look for that level of height. We're looking at flow. So QMed, absolutely, yes, you should be looking at QMed. That's at the moment with DEFRA and EA, the current studies in science around hydrology are saying QMed is the better one to use. If you've been doing QBAR, which is the sort of the mean, it's better to use the median. So you want to use QMed. For those that don't know what I'm talking about or are like, what? The catchment data that we've currently got is very high level. It's just the start. So when you're doing very simple designs, it's a good place to start. If you're doing high risk complex drainage systems, you are better to go and actually get a designer to do your catchment modeling, because it will be bespoke and very focused and specific. For us, looking at the network, 22,000 kilometers of railway, we had to make some decisions where we were trying to be conservative in what we put in. The conservative, when I say conservative, we conservative for us is we took the higher Q value, not this lower. So we're actually showing more water. And also we are putting a lot of sort of general things around when it comes to the soil type, blending soil types and saying this is the majority of the soil type, so we're taking that soil type. But when you do a much more specific focused one, you can get a lot more detail. So I would say it depends what Q, when you use Q, it depends on the type of design. Simple designs, you could use QMed, the catchment model that we've used, you could use that. But if you're doing anything complex or in an area that is high risk, it warrants doing its own catchment analysis and design.
Yeah. So Village Silapan Suthan, and I apologise if I've mispronounced that, actually makes the comment about a cubic metre of water is 1,000 kilograms or a tonne of water, as well as the bathtub.
Yeah, it's very hard to visualize because obviously it doesn't come in a chunk. So people are like, how do you know how much water that is?
Yeah.
If someone's got a better way to describe, I'm more than happy to steal your description.
Right. Yeah. So Daniel Pike has said water has always been the biggest enemy of building or running a reliable railway. Oh, and I can remember when I first started on the railway, I was told the expression aim wide. So aim is arrest initial movement, and wide is water is deadliest enemy. So, so Peter Alford said, you are looking at are you looking at existing discharge rates or introduction of installing additional attenuation? Plus, what is the view of the water authorities if we increase discharge? Will they allow higher discharge rates?
Oh, two very, very good questions, Peter. Right. So as far as the attenuation, when we did the catchment modeling, we had to level out any dimples and so forth. So we are looking at existing discharge rates. We are not, these are not with any modeled attenuation or retention ponds. This is just looking at some level of saturation. And if you're very interested and you want to know a lot more detail, the person, I'll give you his name at the end, is my technical lead, and he is a hydrologist. And we also brought a geohydrologist in and and we got lots of clever brains to work on this, on the modeling. I can send you some documentation on what we did and didn't do. And when we looked at our catchment analysis, I'm more than happy to share that with you, Peter, if that's something that you're interested in looking at. If you pop in the chat, let me know and give me your email. I will send you our discovery phase report on the things that we didn't look at. Now, from the water utilities, that's a very interesting question because it depends. In Southern, Thames Water want our water. So because of the too much, too little. So it all depends. And this is where those catchment community projects have to come in together, because we can't just quickly discharge all the water onto the rail off of our land and go, not our problem anymore, because basically we literally are just pushing the problem downstream. And our neighbor upstream could be doing the same to us. So really it's about looking at the catchment as a whole and everyone that's affected there. Someone might want your water. It might irrigate their crops. Someone might go, no, we've got the same problem. We need to get this water away. How best to do it? And so it genuinely just depends on that. Plus, you don't want to have such high volumes and frequency flow rates that you create scour or erosion, because that's the other thing, that water does do that. So we have to be we really need to be a good neighbor and a good catchment in the catchment communities to look at the right solution across the board, not just high velocity, get the water out, because it's not right.
No, people regularly do that to us, and it causes us a lot of problems.
Yes. And we're reaching out and saying, let's be friends on this whole thing and sort these issues out together. Yeah.
Emma Norman says, in PFL, we have areas where we are the infrastructure manager for track used by Network Rail TOCs. If we need to get catchment data for drainage modification works, should our project DPE contact within Network Rail be able to provide this as a more direct route than submitting an FR?
Yes, Emma, totally yes. Anybody in Network Rail, everybody in Aspro, anybody in property, everyone in Network Rail has access to GeoRhythm Viewer. It's a free tool that you just go into what's called My Connect, and you could type GeoRhythm Viewer, and then the tool comes up. And all they need to look for is drainage is at the top, and right underneath it, it says catchment layer. And they just activate the catchment layer, and then ta-da. And if they're really clever, they know how to export that geospatially and all that good stuff. But yes, absolutely, Emma, that information is available for anyone, any contact that you've got within NR. And your DPEs can contact the sponsor, they can contact the local depot, they can contact. And if you're really stuck, that's really the freedom of information is sort of the last resort, because it's a bit of a pain, only because you have to wait. But yeah, anybody in Network Rail has access to that data, GeoRhythm Viewer.
Okay, Paul Abbott asks, do we in the industry need to do more to help our operating colleagues, brackets, and politicians, close brackets, to understand the challenges with water and earthwork slopes in a simple way?
Yeah, oh gosh, definitely. And that's why I put that statement in, that drainage is simple once you understand the complexities, because I think that previously we've oversimplified it. We thought, oh, it's just easy, it'll just be fine. It's not fine. 2 rules of water: it flows downhill and it follows the path of least resistance. That path of least resistance could be through your rock cutting and it'll take all of it with it. That path of least resistance could be through your cable troughs, through a substation, through a car park. That's not what we want. We want to manage it. water cycle is happening. We want to manage it. What I'm hearing through my industry and what we're hearing now, it is coming. Water footprint. We talk about carbon footprint. Conversations around water footprint are coming. So they're starting to be more, what is your water footprint when it comes to doing things? Also, we're hearing a lot more around legislative change to require more sustainable drainage systems being put in. SUDS, if you're familiar with SUDS, legislation is going through the Flood and Water Act to say that everyone has to comply. It's an interesting one because for us, we're like, wait a minute. We want to do SUDS, but we don't want somebody to tell us what SUDS we have to do because we have to manage the railway. So it's a very interesting consultation that's going on in legal terms. I shouldn't say this because this is being recorded, but politicians don't really respond until it's really late, like they do with sewage discharge. So now every politician's talking about sewage discharge and carbon, footprint. It's like, God, so late. So really the key is our designers who are thinking about what we're going to put in the ground, and our suppliers and manufacturers who start to challenge. We need to start challenging them, saying we want blue-green solutions. We want solutions that don't need maintenance. We want solutions that are fit for purpose. That's really where the changes are. If you want to start championing it, that's really where we got to go.
Right. Okay. Yeah, I don't think politicians ever look further than the next election, do they? But right, Emma says thanks. Daniel Pike says, whilst improved designs and better information are valuable, implementing drainage changes are typically slow, yet our problems are current and increasing. What is being done to prioritise schemes, and are monitoring of current assets also receiving the same attention?
Oh gosh, Daniel, yes. So everyone's tightening their belts in CP7 for just everyone's struggling with money. And Network Rail are no different. The impact of COVID and less passenger travel, or different changes in passenger travel, less revenue, is affecting everyone. So everyone's squeezing the belt where they have to. I am flying my flag as hard as I can, as high as I can for drainage. The thing to me is around education and understanding that you can keep addressing wet beds, but the clue is in the name. It's wet. So to sort your drainage out, you can then won't have wet beds. We can look at putting sandbags up and building retaining walls because earthworks is moving. But again, if we could put proper drainage in and take the water away from the earthwork, take the saturation levels down, we wouldn't have as many of those earthwork movement slips. And the accent gives it away. I am English. I was born in the UK, but moved to California, where water is so precious. So being a civil engineer from California, everything we did, we thought about water, car park design. Where's the water going to go? Where's it going to come? Housing, everything. And I don't know if we just got relaxed in the UK because we always have water. Water is always here. But things are changing. Now you're getting more water than you had before. And not only that, you're not getting water. Oh, that's weird. 40-degree temperatures, land drying out. And so there's a challenge. We have to change our attitude towards it. And it's collaboration and partnership. It's working with drainage and track, working with earthworks and track, working with structures and drainage, saying, come on, let's together work this through. So going into CP7, we are seeing an increase in operational funding for drainage because our inventory is being increased, and it's increased because we didn't have a complete one, and now we're working on complete our inventory. So matching that is the resources supporting that increase. But also, and then it's unfortunate to say, we had a wake up. We had a wake up with Carmont that drainage isn't just something that, I was just a pain. There was an extreme and adverse weather event. The drainage system could not cope. The drainage filter material landed on the track and we derailed a train. Now, could we have seen it? Could we have done all that? Well, it was nothing unusual when it came to the design of Carmont that was in anywhere else. But it's not acceptable for people to lose their lives. And that wake-up call is making a lot more people talk about drainage and what they should be doing in drainage. And so going into CP7, financially in a better position than we were in CP6, but it's tainted, and it's with a dark cloud over it, pardon the pun, but we will be better. We will be better, and we will get better. And we need to start to prove that if you sort drainage out, your infrastructure will be stronger as well. So sorry.
If I could add to that, Mona, I think the other big difference is now is we are much more aware now of the consequences of not dealing with drainage.
Yes.
In terms of train performance and disruption and things like that. I think we're a lot, we've collected a lot of information now, which is helping to drive the business case. So
yeah.
Right.
And I like root cause analysis. Why do we have a twist fault? Why do we have track geometry problem? Why do we have a wet bed here? Keep asking the why, and get to the root cause and deal with the root cause so you don't have the repeat problem. Repeat flood locations is just the bane of my life. Why do we have repeat flood locations? We should get to the root cause, which might be outside of our boundary, but much more conversations happening. Yeah.
Right. So Peter Alford has actually said again, he's put in the chat, he's put his email address and says he's CPD, now he's retired. He would very much like to be kept in touch with what's going on.
Yep.
Brian Dunmore says thank you very much. And so does Philippa Murphy. Says thanks very much for a really interesting presentation, Mona. As a non-engineer, you made this technical topic very accessible and understandable.
I threw in some equations for you, Philippa, just so you could pretend to talk the talk. That's okay. Most of us do the same too. So I'm glad it wasn't too technical. Yeah, it's very hard to judge sometimes. So yeah, pleasure.
All right. So as it's nearly past now, so thank you again, Mona, for your presentation today. I've certainly found it interesting, and for me, in the industry, I think drainage is now much more professional rather than something which is a bolt-on. It's now seen as a key part of the railway system, and I think that's really important. So can I ask everyone to unmute yourself and thank Mona in the usual way?
Bless.
Thank you.
Thanks, everyone. Thank you.
Thank you, Mona. Very enlightening.